Ladies and gentlemen, please take your seats. The first speaker of the late afternoon session is Professor Daniela Bortoletto, who will speak on detector R&D.
Thank you. I hope that you can hear me well. And my session covered more or less a lot of the R&D that was going on for all of our physics. We had presentation from Atlas and CMS going towards then the energy frontier to the machine of the future. Then presentation on the intensity frontier with detectors that are already taking data and detectors that will come up in the future. And then the cosmic frontier, the search for dark matter and dark energy, was covered in another session. Nonetheless, it was very difficult to cover this session and to give relevance to all of the work that was presented here. We had about 94 talks in this session, and so I will not cover any of the running detectors, with the exception that I wanted to show these plots from Bell 2. Obviously, you know, here is the first hadronic event that was recorded in April of 2018. And here is a BB bar-like event. So Bell 2 has started. And therefore, I will focus a little bit on the newest development, and I will try emphasizing the connection between the various communities. And I apologize for the many important R&Ds that I will not cover in my session. So if you look at this timeline that you have seen many, many times during this conference, here is our road to our luminosity. We are about here. LS2 is about to start at the end of this year, and then we'll have a long shutdown for the ILUMI LHC in the mid of the next decade. So there will be a lot of activities for the LHC detectors during this period. And again, they are shown here. And again, apart from the complete replacement of some of the tracker, we will also have to introduce a lot of new electronics, trigger system, new DAC, and ad hoc elements to make sure that everything functions in this very challenging environment. So actually, the first upgrade that is going on is going to be the LHCb upgrade that is coming on really during the next shutdown, LS2. And you can see here that one of the most challenging detector element is going to be the Velo upgrade, that is a vertex detector for LHCb. And you can see here that, again, some of the conditions that LHCb will have to stand are actually quite similar already to ILUMI condition at about a level of 8 times 10 to the 15. And you can see also the improvement that the new upgraded detector will give with respect to the current one in terms of the resolution of the impact parameter. So again, a lot of good new physics will be allowed by this detector. From the technology side, the most remarkable aspect of this technology is actually the fact that the cooling will be done with a technology that has never been implemented in experiment at the LHC, which is called microchannel cooling, where microchannel are made in a silicon substrate, which is about 500 microns thick, and therefore can provide very good cooling to the very close to where you have your circuit, your redoubt rock that dissipate most of the power. So you can see here that they are fairly advanced in the construction of this detector. Also for particle identification, LHCb will do a lot of upgrades to their ringed imaging detector, which provide particle identification. For example, already in this shutdown that is coming up, they will replace the photodiode, and they will go from hybrid photon detectors to multi-anode PMT, which are produced by Hamamatsu, which are able to operate at the 40 megahertz rate that is necessary for this experiment after this shutdown. Then for LS2, they will implement torch with a time of flight internally reflected Cherenkov light, which will provide a time resolution of 10 to 15 picoseconds. You can see here the particle impeding, and the photon will be transmitted, and the time of propagation can be measured with these microchannel plates. And you can see that for the first time, LHCb will have identification of kaons below 10 GeV in momentum. So really opening again new physics for the experiment. The truly amazing environment will be really the ILUMI LHC, where we will have about radiation level. Here is a map of Atlas and the radiation level in terms of fluence. You can see that you have a zone where you go up to 10 to the 16 nearby the interaction region and towards the NCAP. And also total ionizing zone of the level of 1 megarad, so very high, and pile up of 240. Here is an event collected by CMS with a pile up of 100. So it will be much worse of what we do now, that is about 50 in terms of pile up. So we will have to replace all of our trackers. So here are the tracker concept for Atlas, and here is a track concept for CMS. As you can see, they are slightly different. The concept of CMS with these double layers, it's motivated by the level 1 triggering concept, while instead Atlas has really gone for a very large pixel, very tiny pixel region. And again, one of the things that are common to the experiment is that there is an area nearby the interaction region where you have higher dose and higher radiation, where you can extract this layer very, very fast. You see that also both experiments have gone to an inclined geometry that is different from what we do now. And you have all on NMP sensor as a baseline, which is allow you to a undepleted collection of charge, and you collect electrons, which are faster mobility. 3D sensors, though, where you are implanting the implants inside your silicon bulk, are going to be very important probably for the innermost layer of the detector, maybe the first two. But again, the experiment have to still take a decision about that. In terms of this detector, are going to be both hybrid detector. So you're going to have, and we have demonstrated that, so hybrid detector means that the sensor is connected to the electronic by band bonding technology, as you can see here. And both technology, both the planar and the 3D, has demonstrated to be radiation hard up to the necessary 3 times to the 16 in terms of fluence. You can see here in terms of 3D that you are up with a voltage of about 150 volts. You are already almost 98% efficient after almost 3 times 10 to the 16, so a very high dose. And again, the hybrid detector will be read out by the RD53 chip, where a joint R&D was conducted by CMS and Atlas in 65 nanometer technology to get this project up. And then the R&D will split now and to make 2 chips, one for CMS and one for Atlas. The real technology changing, game changer, is going to be the implementation of monolithic technology. Here is, for example, the Tower Jazz chip that is a sketch of Alpide, which will be used in ALICE tracker upgrade to be installed in LS2. And the change of this technology, you can see that you have an epitaxial layer of about 30 micron that will give you a charge collection of about 1,600 electrons. And because of the insertion of this deep N-well, your electron will be collected only by your N-well collection diode, which has a dimension of a few micron, giving you a capacitance of a few femtofarad. Really a fantastic detector. And there is a lot of enthusiasm towards this technology. And we are trying variation of this technology with different companies, L Foundry, AMS, Tower Jazz. In fact, this chip here, called Malta in Tower Jazz, the name stands monolithic pixel sensor from ALICE to Atlas. So you see the connection in the field. And these depleted CMOS detectors are going to be very important for the LHCb phase 2 upgrade, for future machine like FCCE, CPC, CLIC, etc. It's a direction that the whole field will go. We have done, in terms of the Atlas CMOS demonstrator program, you can see that there are several achievements in terms of radiation hardness fluence, up to 10 to the 15, you can see here. We get 100 micron depletion region. With AMS, for example, you see that before irradiation you get 99% efficiency. And you can see that even after irradiation, the timing is very fast for this technology, to less than 3 picoseconds. So, I told you at the beginning that the design of the CMS detector was motivated by the tracking at level 1. So you see here that by having 2 layers of silicon that are close by, you can distinguish tracks that have low momentum from tracks that are higher momentum. And the idea here is to do the tracking using these tracklets very, very fast, within 3 to 4 microseconds. And there are a couple of ideas that are under study. But all of this information will be available at the FPGA level. And then this will give you a lot of freedom. For example, there are promising extensions towards displaced tracking. Here is a tracking efficiency versus the impact parameter D0. You can see that you can go up to 3 centimeters with 4 layers, and you get an efficiency of about 60%. You can implement machine learning techniques to discard fake tracks, and you can you can work towards an all FPGA solution. And you have like 10 years, to work towards and take advantage of the improvement in FPGA technology. So, So you can see here that in terms of the fast tracker, yes, okay. That Atlas is also implementing this fast tracker, which is due to a different technology. So you are going to have, looking at the information given by only by the silicon now, comparing it very fast with a pattern that you have stored in a memory, and then collect all of this information to perform a linearized fit of the tracks, again very fast. And this system is already 50% ready to be tested in Atlas this year, and then the other 50% will be tested during the long shutdown, and then the whole system will be in operation after the long shutdown 2 in run 3. So timing is becoming very important for the LHC. You can see here that if you have like the vertex information, a lot of vertex are overlapping because of the pileup, but you can distinguish them if you take in account the timing information, if you get a resolution of about 30 picoseconds. So you're going to have timing layers at CMS, all around for a full hermetic coverage at eta less than 3. And so you have a barrel layer with LISO tiles and an IPM readout, which will be mounted on the support structure of the tracker, which will be integrated in 2022. And again, you have also end caps with low gain avalanche detectors on the calorimeter. This is the same technology that we'll also use for Atlas. And this technology, again, is quite interesting. In a low-gain avalanche detector, you have an extra implant in your usual diode that creates a very high region of electrical field and creates multiplication of your signal. And then if you couple with a good readout electronic, you can achieve really excellent timing. And you can see here that work has been done because the timing is impaired by irradiation. And you can see here that we have done a lot of work, and you see that even after 50 picosecond, even after 10 to the 15, you get about 50 picosecond timing resolution. And by having a few layers, a few points, you can achieve the 30 picoseconds that you need. And again, the chip has been matched to this technology. So I feel like I'm going very slow, and I have only 5 minutes. I just wanted to show that, there is R&D towards thinner detectors, which achieve, you see the resolution, the timing resolution for thinner detector is better if you go below 50 micron. And again, you can do different coating with boron carbon to achieve, again, better radiation damage. So the particle flow calorimeter is something that came from the ILC, and is going to be implemented in CMS with, again, these layers of silicon, with this layer of silicon and copper tungsten plates. And also with scintillator tiles with on-tile CMS readout. Again, they are ready for a lot of they've done a lot of study in beam test of this technology, and everything seems to be working as expected. In terms of what has been done for the LHC, a lot of work has been done also for material reduction. You can see here again the carbon fiber structures that are used for the supporting of ALICE detector, extremely light. For Atlas ITK, all the module support is done with a copper capped on co-cure tape with embedded CO2 cooling. And there are other development in terms for other application, like for the mu-free detectors that is looking for the muon decay into free electrons that is not expected in the standard model. And you can see here that this detector will be almost be Kapton. So you have a layer of Kapton that supports your chip, that will be these depleted CMOS detectors. And then the cooling will go in a small channel, which is made up with another Kapton layer. And again, there are a lot of development of materials that will come in the future with carbon nanotubes and graphene, which have unbelievable coefficient of thermal conductivity. So here is a summary of all of we have to do for the future. So very large detector, gigantic, and detectors that are going to be very challenging because you will have to reach a very low material budget of 0.1% of the radiation length. And so all of this R&D that is going on in different experiments will be useful for the future. So going to neutrinos, we have, the neutrino beam from Fermilab will be pointing to the Dune cavern in South Dakota. And the technology of choice here is liquid argon technology, both single phase and double phase. It gives you this enormous capability of reconstructing tracks. And there is a lot of R&D. The excavation has started already last year in July. And there is a lot of R&D going on for the liquid argon with very large detectors that are under assembly now at CERN. Like, for example, here is the proto-Dune single phase and the proto-Dune double phase. And all of these, the assembly of these big detectors will allow you to test all of these technologies in grand detail and be prepared for this large jump of size that will be required. In the case of Hyper-K, the detector is a water Chelecon detector, which is about 10 times the fiducial area of Super K. And the innermost volume is viewed by 40,000 new 50 centimeter PMTs that are produced from Hamamatsu. You can see that the Hamamatsu has already a couple of prototypes that have been already installed in Super K. And you can see that the performance of the hybrid photodetector is in fact much better than the one, for example, that are used in Super K now. There is also a lot of work for this newer detector technology because you have to do really a good measurement of the flux before the neutrino reach the far detector in order to measure CP violation. And there is a lot of technology, for example, looking at having liquid argon for Dune and having a water Cherenkov detector for hyper-K in order to have a cancellation of the systematic error. For Juno is, if you want, the next step after Diabase, and to measure the neutrino mass hierarchy with a good sensitivity after 6 years. And so it's measuring antineutrinos coming from a reactor. It's about, the central detector is about 20 kiloton of a liquid scintillator, which will achieve unprecedented energy resolution. And the light detection is done by almost 20,000 photomultipliers. And 75% of them will come from a Chinese company, and the remaining will come from Hamamatsu. So you can see here the concept of Juno. You see the big PMT, which are 20 inch in diameter, and the small PMT. And they have already received about 10,000 tubes, and they have created an assembly facility in Zhongshan near the Juno site in order to have a systematic measurement of the properties of all phototubes. And you can see here the performance of the phototube from NVT in red and Hamamatsu. They are quite similar. And you can see here the facility, some of the testing facility where they do the testing. The amazing thing is, again, that there is a progress to the establishment of this very large phototube. It's been phenomenal. There were ideas in 2009, and now there is production. Another new idea that is moving fast is the idea of the large area picosecond photodetector, or LAPD, which provides a large area photodetector, which is being made possible by using atomic layer deposition coating to convert this glass in capillaries array into microchannel plates. And you can see here again that we have gone from an idea a few years ago to a detector that's been installed already at the Massachusetts General Hospital for proton beam testing. And it has a variety of applications for this detector. One of the things that I would like to mention are silicon PMs, because there has been a lot of understanding of the physics behind how silicon PMs are working. So these are arrays of photodetectors operating in Geiger mode. And you can see that the company have achieved a great reduction in crosstalk. Here are some silicon PM from K-Tech, a reduction in crosstalk of about a factor of 3. The use of new transparent resistors that let the UV, glue, and green light going through has given the possibility of measuring, for example, here is, for example, the photon detector efficiency for a SIPM from Hamamatsu with 515 nanometer. You see the increase here in photo detection. But also now we are going to ultraviolet, which is very important. For example, here is another photo detector from HPK, which is sensitive to 150 nanometer for detection of liquid argon in scintillation light. So very important changes. Again, there are a lot of companies doing SIPM, and in this conference, a lot of experiments are using this technology for various applications. And as you know, these SIPM are going to be very important for the LiDAR technology for automatic driving. So I would like to conclude by showing you some physics that is going on here in Korea, and I have 1 minute apparently. And it's ongoing, and it's going on at the Center for Underground Physics, and the experiment is called Amore, which is a good name to end my talk, isn't it? So it's an experiment for searching for neutrinoless double beta decay using molybdenum 100, and they can grow the crystal, and they redact the crystal both phonon and light by using some metallic magnetic calorimeter and operating at 10 millikelvin, achieving KV energy resolution. The nice things about this detector is that it can be stuck very easily. This is a pilot run that they've done with 6 crystal, and they're planning to go up to 6 kilogram in 2018 and to 200 kilogram in 2021. And again, the limits that can be putting are around, the inverted hierarchy level for neutrinoless double beta decay. So very interesting region. So I would like to conclude by saying that we are in a very much data-driven era, and that the exploration of physics beyond the standard model requires these new detector techniques. And very often, new detection in science are launched by new tools more than by new concepts. So we really have to do new measurements. And thank you, Gamsahamnida, to the organizing committee to invite me, to the people who gave talk in the parallel session, to the convener of the CERN-EP departmental R&D on new experimental technology, and to a couple of people that have provided information. And also, I would like that we remember that all of these results can only be obtained by the labs providing the facility to do a lot of our testing and our irradiation. Thank you.
So the next speaker is Akai-san from KKD, who will speak to us on accelerators, mainly Super KEKB.
I'll talk about Super KEKB and Bell 2 status, mostly on accelerators. And my talk mainly consists of 2 parts. The first, upgrade overview. The second, beam commissioning. So this is KEK Tsukuba site, where Super KEKB and Bell 2 are located. The predecessor, KEKB and Bell, has generated many important results, including experimental verification of Kobayashi-Masukawa theory. In order to search for new physics beyond the standard model, a complete upgrade to Super KEKB and Bell 2 started, and after a large-scale construction completed, we started physics run operation this year to pioneer luminosity frontier. This is the overview. The Super KEKB is an asymmetric energy double ring collider consisting of 7 JeV high energy ring for electrons and 4 JeV low energy ring for positrons. The beams are delivered from injector linac and positron damping ring. At the interaction point, Bell 2 detector is located. And the beam energy, center of mass energy, is adjusted to epsilon resonances. So I'd like to mention here energy frontier and luminosity frontier. So there are 2 types of experiment. One is direct generation by high energy collision. The other is a precision measurement using the so-called tunnel effect. And for the energy frontier machine, beam energy has been increasing higher and higher, and now LHC is world leading. And for luminosity frontier, although energy is lower, so-called factories, the luminosity has been increasing about 1 decade per 1 order of magnitude per every decade. So super KEK-B is aiming at 40 times higher luminosity than KEK-B. So I'll go to the first part, upgrade overview. So KEK-B operation stopped in 2010, and we started upgrade. And these pictures are to dismantle KEK-B rings. A number of components were removed for the upgrade, while others are reused as much as possible. This is the overall schedule. The upgrade construction continued for about 5.5 years. And after low energy ring and high energy ring construction was completed, we started phase 1 commissioning without collision. After that, the interaction region was renovated by installing superconducting final focus magnets and belt detector. So after these works completed, we started phase 2 commissioning for beam collision. And now is at the end, close to the end of the phase 2. After phase 2, vertex detector will be installed in innermost of the belt detector. And phase 3 will start next year with full belt detector. So we adopted so-called nanobeam scheme to increase luminosity. In usual collision scheme, either head-on or small angle collision, the vertical squeezing is limited due to so-called hourglass effect. And by adopting the nanobeam scheme, which is to collide very thin bunches with large crossing angle, we can avoid harmful beam-beam effect due to the hourglass effect. So we can squeeze the vertical beta function at the interaction point below the limitation of the usual machine. This is the luminosity formula, simplified one. And 3 important parameters are beam current, beam tune shift, and vertical beta function at the IP. So these are the super KEK-B design parameters. If we compare with KEK-B achieved one, vertical beta function squeezing is about 1/20 that of KEK-B. And the beam current will be doubled that of KEK-B. So luminosity will be 40 times higher than KEK-B achieved. And in order to realize the nanobeam collision scheme, 2 points are important. One is lower emittance in the ring, and the other squeeze strongly at the interaction point. For that, not only the interaction point, but also whole ring and the injector linac need to be upgraded. So I'll quickly go through major upgrade points next. First one is the magnet system. In order to achieve lower emittance, we replaced bending magnets at the arc section for LER, and we reinforced regular sections in both rings. In addition, both sides of the interaction point, the beam line was completely renewed. One of the most challenging one is final focus superconducting magnets. This is really a state-of-the-art superconducting magnets, 8 main quadrupole and 3 cancel solenoid, and more than 40 collectors are included in very tight space, and it needs very precise designing and manufacturing. So from the R&D phase, it takes about 10 years or so. And last year, the superconducting magnet was completed and installed in the interaction region. And they are connected to Bell 2 detector successfully this January. I'd like to mention about the so-called electron cloud issue. So for positron beam, this effect is may be very serious. And for supercake B, we made various countermeasures. For example, we replaced almost all beam pipes in the ring with antechamber type ones, and also TIN coating inside, and various other techniques we adopted. So we believe we had very successfully made a countermeasure. For increasing the beam current twice, the RF system is important, and superconducting cavities and normal conducting cavities, which proved excellent performance with the high beam current in CAC-B, is basically reused with necessary improvements and reinforcements. So as for Linux upgrade, I'd like to mention 3 points. One is we have developed RF electron gun, and the second one is we improved positron target. So these are necessary for high charge, low emittance beams are required for injection into supercake B. Another thing is simultaneous injection to 4 or 5 rings, not only for supercake B, but also to photon factory rings. So for 4 or 5 rings simultaneous injection pulse by pulse, we have installed pulse magnets in the Linux sectors. And the damping ring was completely new from scratch. And the circumference is 135 meters. This is to reduce the positron beam emittance before injection into a low energy ring. So for the accelerator development, we owe many international collaborations. For example, for superconducting final focus magnets, collector magnets were made, and also single-thread wire alignment system was made under collaboration. Also, bunch-by-bunch feedback system, designing system, and collimators were developed under collaboration. So next, I go to briefly explain the Bell 2 detector. So from outer to inner, this Bell 2 has K-long muon detector, and 2 types of also calorimeters, CSI calorimeter, and 2 types of particle identification. One is time of propagation counter, The other is aerogel rich. And central drift chamber, and two types of vertex detector. One is depth FET, and the other is silicon vertex. So these detectors needed to be improved from Bell. Although the solenoid and the mechanical structure was reused from Bell. Bell 2 group has wider than Bell group, and then now has 25 countries, regions, and 110 institutions, more than 800 researchers. Bell 2 was implemented in recent years from outer to inner, like this, KLM, top, CDC, backward ECR, and last year, April, Bell 2 was rolled in, and A-rich and vertex detector. Okay. And as computing, worldwide distributed computing model like LSC experiments, more than 20 countries, regions, and 60 sites. So as you can see, the scalability challenge and stable production by the experts has done, and now the phase is shifted to offshore production. So I move to second part, beam commissioning. Prior to phase 2, we had phase 1 operation for main wing and no collision. So, but the purpose was to make good condition of the LER and HER before installation of Bell 2. And for 5 months, 2 years ago, beam currents increased like this. And another one is beam commissioning of damping ring, so which occurred this January. And phase 2 started in March this year. Main purposes of phase 2 commissioning are first, verification of nanobeam collision scheme, achieving luminosity of order 10 to the 34, and have clear path for further improvement. And another one is examine the background to verify that we can install the vertex detector to start phase 3. And commissioning was successful, and by the end of March, both beam storage was successful. And April 26, we observed first collision. So this is a horizontal beam kick observed in accelerator, and this is a vertical beam kick. And after we adjusted colliding beams, Bell 2 was switched on the observed first event. After first collision, we squeezed the beta function step by step, like this. So, which was already shown last week by our colleague, from 8 to 6 to 4 to 3 for vertical beta function we squeezed. And this table shows only so-called standard operation with nominal beam current for comparison. Higher beam current operation was not shown here. And after first collision, we squeezed the beta from 8 to 6 to 4, but in the early phase, 10 to the 33 was obtained successfully, but after that, in spite of we squeezed beta to 4 millimeter, we suffered. We didn't have any luminosity improvement for 3 weeks. During 3 weeks, Of course, we did optics correction and various kinds of knob tuning for the interaction point. So single beam seemed okay, but for collision beam, HER beam blow up. And we finally realized the cause. And it was found that much wider range for the IP coupling parameters should be searched than we did, in particular for R1 and R2 parameters. For R2 parameter, before that, we searched only these areas. But after widened this parameter, we clearly saw the increase of the specific luminosity, like here. So this graph shows the improvement before and after this improvement. This yellow one is specific luminosity estimated by beam size monitor. But blue one is real specific luminosity observed. So there was a big discrepancy between them. And HER beam blows up at the high bunch current beam. But after that, after this solution was found, these two are very close, and we improved the specific luminosity. HER blow up was reduced. This graph shows the luminosity performance. The vertical axis is specific luminosity. The horizontal axis is bunch count product times number of bunches. So you can see from beta Y, 6 millimeter for blue one, and for 4 millimeter yellow one, and 4 millimeter after improvement red one, and 3 millimeter for pink one. So you can see improvement by squeezing beta functions lower and lower. And we can increase the number of bunches by increasing total beam current. And if we increase 4 times higher, this is around target of phase 2. We can, the 10 to 34 is within our sight. This graph summary shows the recent result. Yellow is luminosity. So for the standard operation, improved. And for higher total beam current operation, we recently achieved 5.5 times 10 to the 33 peak luminosity. So luminosity performance summary, we have squeezed beta function step by step successfully, and now down to 2 millimeter operation. The specific luminosity was increased, and peak luminosity we achieved 5.5, 10 to 33, and with increasing number of bunches, so phase target is almost achieved. So this is beam current, and those during phase 2, I don't know. We have some issues. One is QCS quenching occurred frequently in the early phase of operation. But after we have adjusted collimator setting appropriately, and Bell-to diamond sensor beam abort system was introduced, the QCS quenching frequency was greatly reduced, and only twice in recent operation. Another is beam background, but it is more or less safe to go to phase 3. And we'll add more collimators for both issues in phase 3. Finally, data taking and analysis in BEL 2 is going steadily. And in last week, Tanaka-san and many members of BEL 2 collaboration presented some results. And I'll just show some of them. So this is for pi 0, k short, j psi, and phi reconstruction. And this graph shows rediscovering Chan, d star to d 0 pi. The left plots are for reconstructed mass for d 0, and right plots are for pion. So it shows capacity for C sigma. So, and finally, rediscovering beauty. And this plot obtained from beam energy constrained mass reconstruction and comparing Monte Carlo. So very good agreement. So finally, I'd like to summarize my talk and show near future. New era of collision experiment started with upgraded SuperKEK-B and BEL 2. We have verified the velocity performance with the so-called nanobeam collision scheme. Phase 2 will be completed in 17 this month, and phase 3 will start next year. For near future, we will promote developing luminosity frontier for unprecedented area by continuously improving machine performance. Also, the accelerator team will provide a large quantity of collision data to BEL 2 required for physics discovery beyond the standard model. Thank you.
Thank you, Akai-san. Time for one quick question, perhaps.
You said that you have a background source that you don't know what it is, if I understood the transparency correctly.
Oh, okay.
And so now, does this give you any pause about your expectations going forward?
Okay, due to short time, I maybe skipped to explain that. And basically, the background is very much depending on machine operation condition. And it changes day by day, but basically we have improved machine operation condition so that background situation is getting better and better. So for the inner detector, we believe we can safely introduce a vertex detector for phase 3. And one concern currently is now hit rate to CDC current is somewhat larger than expected, but we have not yet identified if it is really a problem or not. But anyway, we can start phase 3, and we can improve machine performance. One improvement will be introducing more collimators. Now, in LER, we have only 5 collimators, so we realized we need more collimators for phase 3, and we are now fabricating 5 additional ones, and will be installed before phase 3. So it helps improve the situation better.
Okay, thank you, Kai-san, for that very complete answer. And let's thank him again. Okay, so now we'll move on to Shin-Cho Lu, who will speak on future E+, E- facilities, including CEPC, FCC, ILC, and CLIC.
Well, thank you very much for the invitation. Obviously, this is a very big topic. I apologize in advance not being able to cover many very, very important concepts, R&D, and development. Now I'd like to first start with the case, the physics case for these E+- colliders, and then I'll focus on the colliders themselves in terms of design and status, the sites, and schedule, and possible running scenarios, and as well as the challenges facing these projects. And then I'll look at the possible paths to actually realize these projects. The physics motivation and advantage of having an E+- collider to probe new physics to study the Higgs. This has more or less been covered very well during this conference, and the Higgs is very unique. It's very simple and no structure at all, and it contains many very important pieces of information: flavor physics, stability of potential, naturalness, and possibly something new along the way. And our questions are around the properties of the Higgs, and elementary or not, any partners, and especially phase transition is really the spontaneous symmetry breaking and self-coupling and possibly new properties. So we really need to have very, very precise measurement on the Higgs and to probe these kind of questions. Now, looking at where it is within the building blocks, and we are thinking perhaps the Higgs, talking to everyone, could be a portal to the new world that we don't know about. And what about its connection to dark matter, dark energy, so on and so forth. And from the CPC pre-CDR work, and people show that through the indirect probe, one actually can probe into 10, 20, and higher TeV range in terms of beyond standard model new physics. So now if we have a Terra Z together with the Higgs, we may be able to probe to improve the electrical measurement by a factor 10 to 50 and indirectly probe 10 to 100 TeV scale, and this will be very, very exciting actually. Now, where we are with our thinking with 125 GeV Higgs, if we have any deviation of the measurement and indicating new physics, we want our gap, our error to be 1/3 to 1/5 of the deviation from the standard model. And however, from what we have learned from the LGC experiment, and the data seems to agree with the standard model pretty well. And it shows, it actually gives us a hint that any beyond standard model physics reflected into the Higgs, the coupling will be very, very small. And if you take Hantal and Gupta's formalism and looking at the mass scale of new physics, and actually what you see is that if you looking at the anticipated precision from the LGC and the sensitivity to a new object would be around TeV or less. And so in that case, in this range has been excluded mostly by the direct searches. Now, to go beyond that, we need 1% better precision to really go to probe the 10th TeV range. So this is a very important argument for the E+- collider in this case. Now, another point is that the hadron collision provides enormous amount of data and 150 million Higgs per experiment by end of the high-lumi LGC. However, the significant signal to ratio, the background is 10 to minus 10 to the 10 in that case, and minus 10 in that case, and power up, all these things, you don't know the initial kinematics. And E plus minus, on the other hand, is the cross-section is well predicted, sub 1% level, and you know the initial condition, and it's fairly clean, and so that if you look at the Higgs graph echelon, you actually can reconstruct the Z, look at the recall mass, you reconstruct unbiased sample of the Higgs you can study. So while we anticipate the precision on the Higgs coupling will be on the order of 5 to 10% at the LTC, and at the linear collider and a circular collider, and we're anticipating something much better in this case. Historically, my postdoc actually prepared this drawing for me. That is, we started with the tau and charm. The charm discovered at the E plus minus and also a proton beam machine. And the tau charge has been studied all the way for half century at the E plus minus colliders. And then we had a bottom, and in the 70s, and it's on the proton beam. And from there, we've been studying at Clio 1, 2, and then the dedicated B factories, and we just heard a beautiful talk from our Super KKB, and they're onto that again, and there's a lot of physics going on. Now the W and Z, and we have a beautiful collider called the lab, we all know, and we really constrained and really discovered standard model experimentally, and then we have top discovered the Tevatron, and we have the Higgs, and we're thinking about to have a clean machine to study this really to move forward. So looks like from the historic point of view, we're due for a high energy E plus minus machine. On the collider themselves, I have a few words, and I'll look at design, organizations, and status schedule, and the physics potential. This is a table from William Zhou, my colleague, and he looked at the 20 years ago snow mass and a fairly long list of possible future colliders at energy frontier. And under the supervision of ICFA, and everything converged to a cold linear collider beyond the LGC. Now, July 4th changed everything, and all these things are being put on the table and being discussed. And after 6 years, and looks like these four are on the table, and the CDRs are being written, and the serious R&D work are being pursued. So that's what I'm going to be talking about. Now, linear side, of course, it's high energy, multi-TV, and utilizing innovations in terms of normal conducting acceleration structure as click would do, and nano beams we heard from KEKB. And for the circular machine, it's very historic. We can store the beams, we can reuse them, and we have a lot of construction operating experience. However, the synchrotron radiation limits the energy, how far we can go, and also introduce instability, and the beam qualities deteriorates when you go to high energy, and that's why we hit a bottleneck when we go to high energy. So these four projects on the table are actually located, two at CERN, one in Japan, and one in China somewhere, we don't know yet. And so we're looking at the energy range. The CPC will stay 90 to 250 GeV, and FCC will go further to a GT bar threshold. IOC is fully capable of reaching half TeV, and possibly, if we have enough money, we can do even higher energy. Then click is really the one that extends the capability to the range where if LGC has the future discoveries, we'll have this machine to give us a very bright future. So this four machine provide an energy range from 90 GeV to 3 TeV. The click machine is a very compact linear collider utilizing the drawing beam accelerator and the high gradients make the machine relatively inexpensive, and also they are prototyping, they're doing demonstration, and also it's right at a certain side going through the LGC, the ring, and stretching from this end to that end around Lausanne has 3 phases. And the 3 phases goes from 380, where you can do a scan around the 50 bar threshold and dedicated run. And then with the input from LGC, you can actually do much higher energy exploration. And so the exerging gradients is very, very high. And the requirement, the beam size is also nanometer beam requirement, and is very, very challenging to move forward. Now the IOC has recently rescoped to begin at 250 GeV at a length of 20 kilometer long, and with the luminosity giving 1.35 10 to 34. Now the real consideration for this rescoping to 250 was that the possibly precision on the Higgs may be deteriorating, and we don't have TT bar at this stage, and will actually reduce the ability for beyond standard model search. However, the simulation work has been shown at this conference that IOC 250 does produce very impressive precision together with the LGC results, and it is really upgradable in energy to really go to probe the beyond standard model new physics. And the site has been chosen in the northern side, and so it's in a very advanced stage. Now the beam size, again, comparing to the click, all belong to the category nanobeams, and the IOC first stage and future stage, you can also see very interesting is that the luminosity is actually going up when energy goes up, and also click goes up as well in this scenario. Now, going to circular machine, and the CPC team's been working on the conceptual design report, and we just had a review 2 weeks ago, and the accelerator CDR will be finalized sometime in the very near future, and it has the LINAC injector LINAC into a booster, and the booster ramps up energy to full collision energy, then inject into the main rings in this case, and it's a double ring the design, and 30 megawatts power consumption cap on each beam. And it's a switchable between the Higgs mode and the ZW without hardware change. It's a magnet switch. And for the Z and W operation, it uses the half of the RF. And also, we discovered that with the lower magnetic field inside the detector, and the luminosity can be increased. So for the Higgs, it's almost 3 times 10 to 34, and the Z 16.6 times 10 to 34, and with the reduced magnetic field inside our detector, and this can be almost doubled, and the W is also very meaningful. And so this is the current status with the CDR and with the design. The site has not been chosen, and the team is very active scouting in China, traveling from place to places. Here, example, where we had the first site, Xinhuangdao. That's also the one we used for the CDR study. And we look at the central China, southern China, and currently we're looking at a site very close to Beijing, and it's a triangular formation with Beijing, Tianjin, and this brand new city China wants to build and to start a demonstration of a future modern city in China. And so along with the baseline consideration at the site and the CDR describe the interaction region and also the injection region. And so what we learned along the way was wherever you go, we're welcomed by local people, government, and very supportive. And so that's very, very good to know that local government are very supportive. Now the FCCEE is a very familiar place, and that's the LTC tunnel, and we have a ring here going through, stay away from big mountains, and one of the options that for this ring to be a EE collider as the potential first step. And also, of course, the CERN is also considered going to PP, and that's not certain at this moment. And it's a double ring, 100-kilometer long design, and it's asymmetric R layout and optics, and so the synchronous radiation will be not towards the detector, and 2 detectors and 2 IPs in that case. And the power limit is 50 megawatts per beam, and just make sure we can pay the bills in that case, and top-up injection as in the case of FCCEE and also CPC, and also the booster synchrotron collider tunnel. And so they have the drawing here. The injector is shown here, and the injection is 20 GeV beam into booster, interleaved feeding between the 2 beams, and continuous top-up to increase the luminosity efficiency. And the luminosities are very, very strong. And for the Z, it's truly a tera-Z machine. And for the Higgs, it's 7 times 10 to 34. And it reaches the TT bar. And it provides a full range of 90 to 365 GeV. It's a very nice machine if it's built. We can really study all the bosons and also the top, and then some. Now, if you look at the 4 options, you look at the luminosity versus the center mass energy graph, and here is the IOC as of the Hong Kong meeting a year ago, and click 99%, click 100%, and also Lumi upgrade for the IOC and here as well. And for the CCEE, and from the Z, the W, the Higgs, and the TT bar threshold, for CPC, they are shown here. And so what you can see is really at lower energy, WZ and up to Higgs, the circulars actually are having the luminosity advantage. And it's also depending on relatively mature technology. And in the long run, a bigger tunnel will give us the option to upgrade to a PP machine to really go to the energy frontier. And also, it's possible with a large high-energy electron-positron collider, people may be able to add a wiggler to produce high-quality gamma synchrotron radiation for nuclear physics for other study as well as a byproduct. For the linear colliders, even though it's rescoped, the IOC study has shown this very impressive Higgs precision and reached 1% or less. And then for the very high energy, the linear collider really go well, and the Lumi upgrade can be even better than what I've shown here. So I'm taking this is from the Franco's presentation in May. So what I can say is the circular and the linear colliders are really ideally complementary to each other. It'd be nice to have one of each. Now, the schedule. We're right here for the click, and basically we are waiting for a decision from the management in this case, and the construction phase will, preparation take 5 years, and construction will end, and at 2035 will be first beam. That's officially the schedule. And so what I understand is the click is started at the completion of the LGC program, and with the input from the LGC. I think it's very important that we incorporate what we learn from the LGC. The ILC is here, and would like to start, it's a physics program, concurrently with the LGC program. And basically before 2035, and it's certainly upgradable to high energy and also with input from itself and from the LTC. The FCC-EE, among the three options, FCC-HH, FCC-EE, and the high energy LTC is shown here in sync with the FCC-HH, and it certainly shows the timeline of 2039. And again, this has to be the completion of the LGC program with the input from the LGC. For the CPC, we have shown here the pre-CDR study that was done. We're in the middle of design, funding, R&D program, collaboration site study, and also in the mid-2020, 23 or so, we'll try to seek approval and decide on the site and go on to start the construction. Again, the plan is to start physics before the end of the LGC program and perhaps earlier than FCC and concurrent complementary to the IOC, and that's the consideration. Now, the running scenarios in terms of data, and the IOC has documented the plan very well, starting at 250, then move on to 350, and then on to 500 with two different scenarios, and all giving the same luminosity as they proposed somewhat 2 years ago, a couple years ago, and to really maximize the physics potential. The CLIC has also very clear luminosity target on the 380, 350, then with the input from the LGC, they'll go to TeV range. CPC, on the other hand, planned 7 years at the Higgs. The goal is to get 1 million very clean Higgs events and at energy 240 at the initial stage, and then 2 years at the Z and up to tera events, and 1 year at the W, and to really constrain these electroweak parameters and the model as well. And then the FCCE has a very detailed plan and lists the physical requirement, the luminosity for 2 IPs per year, and the luminosity, and then ultimately what they accumulate a number of years necessary. So it's a 14-year program with the intermediate upgrade in the plan in this case. Now, the physics performance on IOC shows very impressive anticipations, and also together with LGC input, you can actually go down below 1%. Same thing for CPC, and CLIC provide the TT bar and self-coupling. It's very, very impressive. And FCCEE and self-coupling here and for different couplings, and also looking for exotics. And these are the extracts from the presentations at this conference. Now talking about the challenges, technological challenges, and then how we can realize these projects. So for us, the industrialization and cost optimization for CLIC is something on their mind. RF efficiency and cost, this is true for both the normal conducting and superconducting as well. Luminosity performance verification, so on and so forth. There are many light sources being built in Europe and in China, and people are actually using this chance to train and demonstrate capability, nano beams, and high Q superconducting RF, very efficient klystrons, and so on and so forth. So you can see the design has been optimized for these machines along the way. They're getting better performance, and they're also assuming better performing components. And then the R&D program specified in the CDRs really to be carried out. And so this is shown the IOC parameter demonstration and who is doing what. And this is very nice to see them making progress and making things towards reality. Another part is the high Q for the superconducting RF cavity and really running the machine very efficiently so that you really can afford to run. And otherwise, the electric bill would pile up. And so this is pioneered by Fermilab back in 2012. And this is what CPC would need. And this is what IOC would need, and without doping, with doping, and so it looks like we were busy testing and these things. And eventually industrial scale to make it work, and China actually is exploring and forming the industrial consortium and try to teach the industry how to do these things. Other challenges I won't talk about it, you will know. And then how we can realize these kind of projects. And for the IOC, and IOC 250 is basically ready to go forward and eagerly waiting for a commitment and support from the government in Japan and to begin the next step. And people are always unified behind IOC. And CLIC and FCC are very similar, and it's international project and after the LTC program. In China, however, the possible path is that the government is looking at a major international science project, and they started to have preparations for multi-projects, and one or two will be chosen to be selected in the near term, long term will be more. So this would be likely a path to realize the CPC. The summary, we really have a very strong physics case for high-energy electron-positron colliders to study the Higgs and the ZW with much improved precision and explore new physics with the input from the LGC. And the community is really making great effort and really laid out 4 options for us. The organization, the design, the technologies are very, very impressive. The high performance of these electron-positron machines and clean and unique kinematics of E plus minus events really offers excellent chance for us to explore and to discover the Higgs and the bosons. So I would say continued effort, worldwide coordination, improved design, and technological advance are really critical for realizing future high-energy E plus minus colliders. Thank you very much.
Thank you, Dr. Liu. Although we're slightly behind schedule, you covered 4 international facilities, so I think we should have time for a question or 2. Please.
So while 250 GeV gives you entry ticket into the Higgs club, so there are many reasons to go to higher energies, to study the top and to understand the Higgs potential. So all projects except CEPC have sort of plans how to increase their energy, even if they are starting lower. So what's limit CEPC energy to 250, and are there any plans to increase this energy potentially?
I mean, the tunnel is a tunnel. It's the same as FCC, HH, or EE. And in principle, it has this potential. And it's a matter of time, input from the community, and also to get started to move on to next stage. And so we always think the IOC will be built, and probably better for the IOC to explore the TT bar, and we focus on the lower energy to fully explore the bosons, the Higgs, the W, and the Z. And so that's always our thinking.
Okay, so if I look on the yellow box, I thought that you said well, you didn't say it, but it seems to me that the program for the FCCEE is more than 4 years or whatever, so I'm trying to understand which of those are we supposed to take away from this plot is coming. It looks like there's some contradiction. I mean, because you can't have them in there at the same time, and I think the program for the FCCEE is more than 4 years.
I think, I mean, CERN being at CERN has a full program. Look at the options you have. You really look at the high energy LTC as a viable option. The Hadron Collider, FCCEE, remember, they still have the LTC running, and we'll start to construct the future machine. And so the operation, I don't think is really fully contained my box. It's wide open. It's depending upon the CERN management, the community decide what to do. But this is one of the likely scenarios, I think. Nothing is ironclad, if I understand correctly.
If I may clarify this, these plots are one or the other. And it is understood that the FCCEE would run when the LHC finishes. It can actually run immediately when the LHC finishes, and for 15 years, after which the Hadron Collider would come. Or, on the other hand, if you choose to do the Hadron Collider immediately, the earliest you would be able to do is to start in 2043. That's what this plot says.
Thanks, Alan, for the
Provided
clarification.
you had the money to do it, of course.
Of course.
Okay, thank you, Alan, and thank you, Shin-Cho. We're already 10 minutes behind schedule, so let's thank the speaker again. The next speaker is Jai Yu, who will also summarize two future facilities, this time for neutrinos, DUNE, and T2HK.
Okay, first of all, I would like to thank the organizers for inviting me to talk about these two future neutrino detectors. And most of all, this is my motherland, so I think it's even more meaningful to me. In any case, what I'm going to talk about today is the future neutrino experiment, especially the DUNE and Hypo-K. I'll talk about some introductions and have physics justifications and physics motivations for building this kind of detector. And I'll talk about the DUNE and Hypo-K detector parameters and what kind of capabilities it can actually provide us in order for us to have precision measurement of the neutrino oscillation phenomena. And then that will lead us into some physics potential. So this 25-minute talk cannot cannot do the justice for all the work that we've done. And actually, there were 25 talks at this conference, and it's just impossible for me to cover. So I just picked a few handful of the highlight plots, and then I'll talk about the status and the schedule of the experiments and conclude. So if I were to pick three discoveries relevant to the basic fundamental particle map of the standard model in the past quarter century, it's already quarter century. First is, I would say, the top discovery of the observation of the Topologue, I must say, and Higgs-like scalar boson discovery that was happened in 2012. And then, neutrino oscillation discovery, which actually was confirmed throughout the 90s and the 2000s. Of these two, in some sense, are, sort of supporting the standard model, which completes the map of the standard model, whereas this particular, neutrino oscillation discovery is actually going against it. So we're actually, saying that the neutrino oscillation, the flavor oscillation occurs just because the fact that there is flavor eigenstate and the mass eigenstates differ. That means neutrinos have mass. And since neutrinos necessarily have mass, the standard model does not prescribe neutrino masses, therefore standard model is broken. So that's what the importance of this particular discovery is to me. So that leads us into the physics motivation, where the neutrino sector in the standard model needs repair. It needs to be fixed, and therefore it's very important for us to do the precision measurement of the oscillation parameters, mixing angles and the mass difference, mass square differences, and determined mass hierarchies and so, things like that. And of course, we study the CP violation of the neutrino in the neutrino sector, and also measure precisely the CP phase if there was any CP violation to be observed. And one of the questions is, do the neutrinos and antineutrinos behave the same way when they oscillate away? And these could lead to a new symmetry, which is a very good thing. I mean, it's always a nice thing when there is tension between the experimental discovery and experimental measurement and the theory. And of course, there are lingering questions of the grand unification, where the energy scale, what is the energy scale of the grand unification, and are the, is proton decay? And that's one of the things that we actually started looking into for a long time. And understanding neutrinos from astrophysical origin, supernova and Welling neutrinos, especially understanding how the supernova and the black hole gets formed, looking at the electron neutrinos coming from supernova explosion would be really important thing for us to learn. These require high statistic samples, and neutrinos don't normally, we're not talking about millions of neutrinos, right? I mean, we just heard that there were 1 million Higgs in 7 years, and we don't talk about, and it'd be nice if it would say 1 million neutrinos in 7 years. In any case, so we need large volume and highly capable, both near and far detectors, and high intensity neutrino beam facility with a long baseline. This will allow us to do the precision measurement of all these oscillation parameters. So what's the current status of the neutrino oscillation? So these are all these parameters that we have been measuring throughout the past several decades, and this is the current status of all these different kind of parameters. As of April this year, from NewFit 3.2. The red curve here is the normal hierarchy, whereas the blue curve is inverted hierarchy. The width of these curves represents the current level of precision. So we want to make sure that we can actually reduce that width as much as we can, and that also allow us to determine even the mass hierarchy and measuring precisely these parameters. So in order for us to do that, we have the next generation neutrino experimenter needed, and with the 2013, this is really confusing button. 2013 strategic planning, of the community in the 3 different regions, we actually, the effort of building 2 large-scale neutrino experiments, started in earnest. The first one that I'm going to talk about is the Hypo-Kamiokande, and T2K and T2HK and T2HKK. The second K is actually Korea K. In any case, this is the sort of the picture area view of the Kamiokande area, where we're imagining putting in a Hypo-K detector in here, with an overburden of about 650 meters, not too far from the Super K. This is a joint effort of the teams from all 3 regions, and located at Kamioka, and it's a water-Cherenkov detector, so this is a proven technology. We've been actually building many different size and scale of these detectors before, and it's been running. Okay, and this proto-collaboration, Hypo-K proto-collaboration, consists of about 300 members and 74 institutions from 14 countries. And it's supported by Japanese yen, Japanese supported at the level of Japanese yen 10 million last year, this year actually from MEX, for some fundamental studies. I'm going to talk about it a little later, but this amount don't look large, but it has a lot of big meaning as I would understand it. And it has recently released the design report. That's the archive, the document, and that was in May this year. So it's previous, about a month and a half ago. And this is the overall view of how the T2HK looks like. So here, the beam of T2HK comes from JPOC facility, JPOC high power proton facility. It's 2.5 degree off-axis narrow-band neutrino beam for precision measurement. The beam power, expected beam power at the time of running is 1.3 megawatt beam power. Beam is shot from to Kamioka, which is 295 kilometers away. And at that location, with the overburden of 650 meters, there will be 2 caverns, and with that host 2 water-Cherenkov detector, with a fiducial volume of each of these having 187 kiloton of water in it. And that means each one is about 8 times the Super K active volume. And of course, there is a new detector about 280 meters down the road. And then on top of that, we're talking about beam actually going, neutrinos like to go all the way, right? So that's, I was told that's free. beam is free. So you can actually have that beam if there is a detector of the same size installed here. Depending on which location it goes, it actually sets the different baseline that goes from about 1,000 kilometers to about 1,200 kilometers. And on top of that, depending on where it locates, you actually captures the different neutrino beam energies because the off-axis angle. The second detector that I want to talk about is the DUNE. DUNE stands for Deep Underground Neutrino Experiment, DUNE, and it shoots the beam from Fermilab down to underground laboratory in South Dakota, 1,300 kilometers away. It's a joint effort of, again, team from all three regions, and it's hosted by Fermilab and the US. It has already 1,132 members. We're talking about neutrino experiments that's getting close to the LHC experiment size. Not yet, but getting close. 179 institutions from 32 countries. So, and yes, Korea is in there. It's a liquid argon TPC, and it employs two different technologies, single phase and dual phase. Daniela was briefly touching that in the previous talk. But within one experiment, therefore, it allows us the possibility of cross-checking, systematic cross-check. And it also consists of a long baseline neutrino facility, LBNF, for Farsight facility, whose construction was approved by the DOE in September 2016, and the groundbreaking was done in July 2017 there. So that's a ceremonial shoveling that nobody shoveled anything, really. Okay. So anatomy of a DUNE experiment is that it has a beam. Beam is broadband neutrino beam shot from Fermilab. With the beam power on day one is expected to be 1.2 megawatt and gets to be upgraded to 2.4 megawatt. And then it actually has a long baseline like so, and the South Dakota Underground Laboratory is 1,500 meter underground. It's not the overburden, but it's 1,500 underground, 1,500 meter underground, because it is going to be in the mine that's not being used anymore. So there should be a new cavern, 4 new caverns to be built. So this is a structure of 4 new caverns that will host 4 different cryostats, and each of the cryostats is a dimension. This is just an inner dimension, 65 meters by 15 meters by 15 meters. That's the rough dimension that we're talking about. So we're talking about huge building, and there are 4 different huge buildings in there. And going, directly to this kind of thing is not that easy, because there are a lot of things that we have to do, like scalability and quality control and quality assurance and stuff like that. Now let me just talk about the beam facility a little more. So long baseline neutrino facility, as I said previously, consists of 2 elements. One is the far detector sites, which we call Sanford Underground Research Laboratory, or SURF, in South Dakota. And so that's a schematic diagram of it. That's not meter, but that is feet. And then the neutrino beam line at Fermilab, which was driven by proton that has the energy range that you can have the energy range of 60 to 120 GeV. And with 1.2 megawatt beam power, upgradable to 2.4. And this is how the schematic diagram looks like. And the beam toward the South Dakota is coming out. There, it probably doesn't tell you too much the direction. This is a horn-focused beam optimized for CP violation studies. So it provides access to 2 oscillation maxima. So here is a probability of the oscillation for muon disappearance and electron appearance, electron neutrino and electron antineutrino, as a function of neutrino energy for 1,300 kilometer baseline. And so there are 2, the oscillation maxima that are accessible for DUNE. And this is the expected beam neutrino energy. And as you can see, that it covers the range that these 2 oscillation maxima is completely covered in there. So the financial support is an important factor for this kind of large-scale experiments. And as I said, for Hypo-K, it was supported at 10 million Japanese yen this year, but I was told that actually means a lot more than than what amounts it's telling you, because it actually implicates that you can be approved for an experiments this year. Dune, on the other hand, is going slightly differently. Dune funding support highlights, this is just highlights because there are others who are also contributing to it. So US Department of Energy is the biggest, hosting agency. LBNF, Long Baseline Neutrino Facility, SURF facility construction, the cavern construction has been approved, and that fully approved means that the money is there now. You can actually go and start excavating, and we're talking about $100 million there. And then LBNF neutrino beam facility is to be approved shortly, and this LBNF neutrino beam facility is where the proton hits the target, and then you get the secondary beams coming out, and you focus them, let them go through the decay chain and things like that. That's the part. But then there is also independently the accelerator improvement plan, which we have to have enough proton intensity that needs to be improved so that we can shoot 1.2 megawatt of beam there. That's a separate money, and that separate money is also in there, and US Congress is paying a lot of attention to this, and that's a good thing. Detector construction for prototyping also is in progress, as again, Daniela briefly covered. I'm going to show you a little more in here. CERN is also a very important partner in this, I would say essential partner in this. It has constructed a neutrino platform in the North Area extension. So if you go there, then you will see a lot bigger building. And it built 2 proto-Dune cryostats. So it built 2 proto-Dune cryostats, and it's committed to build Dune cryostats, Dune being the final Dune cryostats there. In fact, the first meeting with the GTT, which is the one that's building these cryostats, occurred last week, as I was told, to discuss about design parameters. And CERN is playing a leadership role in installation of prototypes and also the operation of prototype. And it's just impossible for us to run this without having CERN in there. UK has agreed in September 2017 to award 88 million project grant for Dune. So we're talking about several hundreds of millions of dollars committed for the Dune projects at this point. So here is the neutrino platform. As you saw previously, this is dual phase cryostat, this single phase cryostat, which is sealed up now. And these are the clean rooms that we have done a lot of assembly work to install these detector parts in there. So if I summarize in a table, what's the design parameters look like for Dune and Hypo-K? And Hypo-K actually necessarily has T2HK and T2HKK in it. Dune is a liquid argon TPC with, we are actually planning on going 2 detectors first with the 10 kiloton active volume plus 1 plus 1. That doesn't mean you get buy one, get one free. It'd be really nice, it is. Water Cherenkov, for the case of the T2HK, you have 1 plus 1, 187 kiloton staged and get the second one later. T2HKK, on the other hand, has 187 kiloton detector in Kamioka and another one in Korea, 187K. Here are the beam power and the proton energy and the baseline and the distance from the neutrino target to the near detector, which is, the near detector is very important here. So how do we then, with all these baseline parameters, how does the performance expectation looks like? So here are the neutrino energy, reconstructed neutrino energy from the charge current interactions. On the left-hand side is the neutrino mode. On the right-hand side is the anti-neutrino mode. Top is the electron neutrino or electron anti-neutrino appearance. Bottom is muon neutrino or muon anti-neutrino disappearance. So depending on what these depression or appearance of these structure, the spectrum looks like, you can actually look, measure these oscillation parameters precisely. And the more events we have, the better off we are, as you can imagine. But that's not the only thing. You also have to have a precise systematic understanding of the neutrino flux. And neutrino flux understanding can be determined by a very good near detector. So it's very important for us to have near detector that are capable of measuring these the flux before any oscillation kind of stuff happens. This is the equivalent plot of the dune. As you can see, that the range that it covers is very different because of the fact that the beam of the neutrino beam of dune is a lot more wider, broader range of the energy. And this is a possibility, the physics reach of the CP violation. Left-hand side is the hyper-K, and the right-hand side is dune. And dune actually has stage 7-year case and the 10-year case with the error band that reflects the theta 2-3 uncertainties. And what you see here is that above this 5 sigma line here, and that's the range of the delta CP that you can determine with the confidence significance better than 5 sigma. Ooh, 5 minutes. Okay. All right, and here I want to make sure that the delta CP uncertainty, the resolution of delta CP, precision of delta CP is better than 10 degrees at delta CP equals 0. So we could actually, the dune could do sufficient things too. So here is a mass hierarchy case for the case of the hyper-K, where 1 year versus 6 to 10 years, you can actually reach different kind of significance. And this is for the case of dune, where you can see as a function of delta CP, what's the significance you can do in terms of the mass hierarchy determination. This is in the normal hierarchy. And the more exciting thing is actually the possibility for supernova first. So when the supernova explosion happens, then a lot of electron neutrinos come out, and the dune is actually sensitive to electron neutrinos, where electron neutrino spectrum looks like this, and you see in this different range as a function of time, starting from the burst of the supernova all the way out from 0.05 to 0.25 seconds afterwards, and we have to cover up to 10 seconds although. Depending on different time range, you have a different kind of processes happening, and those different kind of processes will give out different number of neutrinos, electron neutrinos. And as you can see in this particular range, these 3 different lines represent no oscillation case and normal ordering versus inverted ordering oscillation. So you see that there are obvious differences in all these 3 different case of scenarios. So it's very important for us to capture that particular energy spectrum at the time, and also by looking at these progression of these energies, and you can actually see the model of the black hole formations. So, but then because of the fact that the beam power is very high, and because large detector mass and highly capable detectors, we can actually think about doing beyond the standard model, because neutrino oscillation is beyond the standard model already. So for instance, looking for low mass dark matter, where low mass dark matter is created through this kind of coupling processes, and it result in the final state with the WIMP. And this is a preliminary, the sensitivity of dune in the electron scattering final state. And there are these, the list of a lot of different kind of, beyond the standard model physics we can do. And this is a particular area where it, promotes the collaboration between experimentalist and the phenomenologist. And we have a lot of theory colleagues in our collaboration. So for dune and single and dual phase prototype, this is enabled by the CERN neutrino platform. Single phase is simple. Interaction occurs inside the liquid, and the ionization electrons drift horizontally and gets detected in the liquid. Dual phase, and here is schematic plot of the diagram of the single phase. You can actually see 2 different cages of the single phase in here, and the active volume is 6.9 meters by 7.2 meters by 6 meters, and it's actually split into 2 6.9 times 3.6 meter modules. Dual phase is slightly different. The neutrino comes in and interaction occurs, and you drift electrons, drift the ionization electrons vertically, And so at the vertically, and here is the liquid and gas boundary, and using the extraction grid, you push the electrons out of the liquid into the gas, and it's followed by the large electron multiplier, which has the exactly same principle as the gas electron multiplier. So you get the multiplication out of this, device, and you detect them. So it's detected at the top of the volume in the gas phase. Okay, so it has an advantage there, but then there are challenges too. If you want, I can tell you challenges later. It's got 6 meter by 6 meter by 6 meter the active volume, and today, as of this morning, the single-phase protodune requires that this is actually 6 meter wireframe. The important thing is that 6 meter wireframe is the unit of the detector that we'll be using in the final dune. So what we are doing here is completely scalable to the final dune. The final detector button-up is in progress for the case of single phase, and the purge begins any day. I was told that as long as they find no leak today, they'll start purging, and it'll cool down and fill by August 31, and therefore it's going to be ready for beam in September. It's a lot earlier than I was imagining originally. Dual phase protodune, field cage completed. What you see here is the field cage of 6 meter by 6 meter by 6 meters all the way around, and it has been air commissioned. We turned on 150 kilovolts on this, in a smart wiring that you can actually have the operational voltage differentials between the lid and in the field cage. So the timeline, I'm almost done. Timeline for Dune and Hypo-K, it's a little bit simplified timeline. Cavern excavation, Dune is 2018 to 2020. Hypo-K is 2019 to 2024, but this hinges on the fact that the MEX is going to approve the go-ahead of the Hypo-K this year. Fire detector construction then it follows in 2022 to 24. In this process, Dune has to have the technical design report completed by the end of next year, and it has to be reviewed, and it then will be followed with the construction. The cavern has to be complete in order for the field cage, the fire detector to construct. Hypo-K is expected to construct the fire detector in 2024 to 25 time scale. And fire detector fill will happen in Dune 2024 and 25, 10 plus 10. So that's 2 detectors to be filled. And for the Hypo-K, it's 187K active volume. Data taking then is 2025 with whatever cosmics and backgrounds that are coming in, and 2026 with the neutrino beam being shot at there. Hypo-K is expected to have beam data taken in 2026. For the case of Dune, the new detector is to be ready by 2027. Hypo-K and the 280 is already in place, and they're actually thinking about different kind of technologies there as well. So, conclusion, neutrino sector or lepton sector neutrino sector in standard model needs to be modified, and precise understanding of neutrino oscillation phenomena and the parameters, and CP violation in lepton sector is essential. So 2 complementary next generation long baseline detector are in progress with large neutrino target mass. Hypo-K is recognized as one of the priority projects, 7 priority projects that are selected every 4 years by MEXT, and is eagerly awaiting Japanese government approval. That's a statement from the project leader. Dune garners strong financial support, commitment from UK and US and CERN and others. Far side construction fully funded and began in 2017. 2 large scalable, important word here is the scalable Dune prototypes are to start taking data in 2018, and we're actually thinking about doing some physics with it too, because it's got 300 tons each. And construction schedule target, with the schedules target beam data in 2026 for both the detectors. So now let me wrap it up. So what is my wish list for, well, I have wrong wish list, but if I just have a few.
Okay, let's try to wrap up.
Yep.
For 5 minutes.
Okay. Discovery of CP violation in neutrino sector, let me say lepton sector, and a new theoretical framework that replaces the standard model or enhances standard model. Discovery of, well, actually it's LSC, more LSC relevant, but I think it's all linked together. So discovery of the supersymmetric particle, followed by observation of the dark matter. Thank you very much.
Thank you very much, Jay, for this very nice survey and vision of the future of neutrino physics. Since we ran 4 minutes over time, I think we have to defer questions till the party. So thank you again. The next speaker is Elizabeth Sexton Kennedy on computing and software.
Well, welcome. Thank you for inviting me. I appreciate being given this opportunity to speak to an audience that I don't normally get to address. So, going on. Where? All right. So, the outline of my talk, I will give a quick introduction and then give my sort of data-centric view of the long-term future of computing. And then I'll discuss a bit about the community white paper. It is a community of people who have gotten together to talk about software and computing tools for the future. And then a bit about the changing landscape of computing and even quantum computing, and how much of this has been reflected in this conference and my observations about that, and then I'll summarize. So both scientific computing tools and methods in HEP are changing. In the past, it was possible to think about computing needs for a single experiment at a time. So you had the Atlas computing model, and then you had the CMS computing model and others. And the number of participants and their growing requirements now make that something impractical. We have to think in terms of community computing because the size of the computing is becoming much larger. And more sciences, even beyond HEP, are becoming big data sciences. So I'd show you the timelines for some of the big data sciences that you've heard about already. So, a vision. So, international big data science, there's the LHC, there's SKA, there's DUNE, there's LIGO, there's LSST, and they're all big data and sciences. While we know the computing challenges are equally large, others outside of HEP are planning to build exascale compute. Now, it will be a challenge to learn how to tap into that resource, but others are building it. So I list this global picture of HPC, and you see that all over the world, people are planning on building these systems. So international science requires international data movement and storage. Most likely, our community will have to build exascale data to match that exascale compute. And we have to do this along with our partners in other communities. So going forward, the LHC will not be alone in using this infrastructure. In fact, Bell 2 and DUNE have already started using it. And for a subset of these collaborations, I will have one slide each on their data needs, just to illustrate how much different this is going forward than it is now. Okay. So these plots were created at the request of our funding agencies and represent what the needs would be for extrapolating from current practice. So what you see is here the running of the LHC, and then the HLLHC turns on, and we get 10 times more trigger rates, and that translates into a huge integral in volume. And this is just what's projected for data on disk. So we're not talking about data on tape here. This is data on disk. And you can see Atlas also has a similar sort of 5 exabytes worth of data in that time frame. So Dune, well, the full stream Dune data, and what I mean by that is if you multiply the front end data taking rates by the number of channels, is impossibly large. That turns out to be, of order 150 exabytes per year. So that's not doable. So much of the detector research that is going on is into reducing that to reasonable rates and levels. So suppression of argon decays, cold electronic noise, space charge effects, argon impurities, they all play a role. And what we're trying to do is avoid having this much data go into it. Above all, that means that most of the challenging data for Dune are doing its prototyping phase now until 2020. So while they're taking the data to learn how to deal with these things, they're going to be taking more of it. So we had a review at Fermilab as to what the computing needs of the proto-Dunes were going to be. And they had low and high estimates of 4 petabytes to 59 petabytes. Now, okay, that's maybe the size of the LHC currently, but they're going to take this data in 2 months. So the rates are really challenging, and the challenge to transport that transatlantically is challenging. LSST will be coming online in the next 10 years, and it too is going to be a data collector of the size of the LHC now. So, you know, the observatory up here in Chile is going to be sending data at 24 gigabytes per second, and then it will be collected in the US and stored. One of the neat things I thought about this was that you can see the old generation experiment, SDSS, and this is the exact same patch of the sky. So you see this red, these dots correlate. And you can just see from looking at it that there's a lot more information density in the new next generation experiment here than there was in the old. SKA is another telescope that is a software telescope. It's very flexible and potentially easy to reconfigure, but it's also a major software and computing challenge, especially with its data rates. It will collect 300 petabytes per year. So putting them all together on the traditional bubble plot, you see that Dune and LSST are up here. Here's the LHC science when you integrate over all the experiments. That compares to the Google search index of 100 petabytes and the Facebook uploads of 180 petabytes. And then as you start getting into the beginning of the 2020s, you see that the data rates are growing, 300 petabytes per year for SKA. LHC will go up to 600 petabytes, and then that's just the first year of running, and so then it will go up even further to 1 exabytes, and you can see how these things evolve over time. Now, of course, the archive of Google data is 15 exabytes, but they have a lot more money than the rest of us. So we do this today with the worldwide computing grid, and it will need to grow. So reliable and performant networking is key to our federated data model. In other words, you know, the way Google can do this is because they have many, many sites, and they are all well connected over networks. And that is pretty much the model that we use in the LHC now. It's just that that's going to have to grow. So usage of this infrastructure will have to expand to support the HEP and other domains as well. Okay. So what have I heard said about this? And some of the things are funding agencies will not buy computing for just HEP anymore. And we can no longer afford to continue with business as usual. So we have reached the end of Dennard or Moore scaling, depending on how pessimistic you are, and what homogeneous resources like the WLCG can deliver. We're going to have to move to heterogeneous resources that are much more challenging to take advantage of. And one of the conclusions of the community white paper is that the HL-LHC salvation will come from software improvements, not hardware. We're going to have a shortfall if we just depend on hardware. The experimental physics community needs to take a page from lattice gauge community, and I'll go into what I mean, what I think the person who said that to me means later. So let me talk a bit about the R&D roadmap. A group of us got together and wrote this roadmap for HEP software and computing R&D for the 2020s. It's inspired by the P5 process and guided by its goals. And what I mean by that is that you had to start with the physics you wanted to do and document that in the P5 report. Then you go on and you design those detectors that meet those scientific goals. And then you think about the computing that you need in order to take full advantage of those detectors that you're designed. And now that we know that, we are writing this paper. It's a 70-page document with 13 topical sections summarizing the R&D in a variety of technical areas for HEP software and computing. So almost all major domains of HEP software and computing are covered. One section on, and then what you see over here, so these are the 13 domains, and then there is a training and careers section, and it concludes. Now, 310 people signed this thing as, to endorse it. And that's covered 124 HEP-related institutions. And this link down here, you can click on it and actually see the full details of the paper. So that paper was delivered in sort of December-ish. And some of it was, expecting certain things to happen in the near future as well, or it was reporting of ongoing work and how to steer it. So we did, at this conference, actually get some elements reported about for some of the areas. And so I can't go over 13 different areas, but I picked the areas that were actually reported on in this conference. So we had a section on simulation, and simulating our detectors consumes a huge amount of resources today. And it remains a vital area for HLLC and intensity frontier experiments. So the main R&D topics for simulation are improved physics models for higher precision at higher energies. And we had a nice talk about that from a GEONT4 developer. So adapting to new computing architectures is another area because, like I said, it's no longer going to be homogeneous grid resources. And so some of the questions you can ask there are, can a vectorized transport engine actually work in a realistic prototype? The so-called GEONT-V project. And how painful would evolution to that be? So we have to investigate that as R&D. Faster simulation. Can we develop a common toolkit for tuning and validating of fast simulations? And how can we best use machine learning profitably here? From everything from using machine learning for particular processes like jet development to what the neutrino experiments do in classification of entire events. And we have had 2 talks about that in the session. So concluding for this area, though, it brought together all the people who work on this area, and they formed a more consistent view and work plan among them. So it was a really good experience for that. So the next area I'll cover is software triggers and reconstruction. So moving to software triggers is already a key part of the program for LHCb and ALICE in Run 3. So real-time analysis increases the signal rates and can make computing more efficient with the storage and the CPU, and allows you to share resources, make them flow between the online and the offline. So the main topics of R&D here are controlling charged particle tracking resource consumption and maintaining performance. Charged particle tracking reconstruction is extremely combinatoric in nature with the algorithms that we have today. And so if you go up to 200 pileup, they become exponentially expensive. So the question is, are there other ways we could be doing this? And can tracking maintain the low piece sensitivity we need to do electroweak physics within the budget? So detector design itself has a big impact on the timing. So timing detectors give us handles that can reduce the effective pileup, as we've seen. And that can make a big difference in the total computing budget. There are track triggers that will make the samples more pure. And then there are layout changes that can be made to the trackers to improve their combinatorics in the software. So improved use of new computing architectures, multi-threading, vectorization, GPUs, and FPGAs will probably have to be part of the solution for this problem. Robust validation techniques then will be really important because we are not going to be homogeneous. We can't just validate it on one architecture and assume that it's going to work the same way everywhere. We're going to have to do validation across multiple heterogeneous architectures, and that will be a challenge. But we have modern continuous integration programs, and these have reasonable turnaround times. This is something the rest of the world is doing as well, and so we're taking advantage of that. And then there's reconstruction toolkits being developed that can act as a basis for these. So these are basic packages that experiments can then take and adapt for their own needs. At least that is a premise of this R&D. So machine learning, there was a lot of excitement at this conference about machine learning. We spent an afternoon on it and had a lot of attendance at our session on this. Neural networks and boosted discussion trees have been used in HEP for a long time, and we've used them for particle identification. But the field has been significantly enhanced by new techniques, deep neural nets, and enhanced training methods in computing. And the move to community-supported Python packages has enabled quite a lot here. And machine learning has been shown to be very good at dealing with noisy data and huge parameter spaces. So there's a lot of interest from our community in these new techniques in multiple fields. So the main topics are speeding up these computationally intensive pieces of our workflow, as I mentioned, fast simulation and tracking, enhancing the physics reach with better classification than our current techniques, improving data compression by learning and retaining only the salient features, anomaly detection for detector and computing operations monitoring. So the red bullets here are the ones that we actually had some reports on at this conference, and you can get a link to them at the bottom there. So I wanted to talk about just briefly another community effort, and that is that there's a group of experts in HPC, who got together with so that's high performance computing that got together with high throughput computing. And one of their summary slides shows that, and this is a direct quote from this report, combining HPC and HTC applications and methods in large-scale workflows that orchestrate simulations or incorporate them into stages of large-scale analysis pipelines for data generated by simulation experiments or observations. So here's the, quote, Internet of Things down here. And a lot of our sciences are taking advantage of these Internet of Things. But then from there, you have to connect that with the high throughput computing, reduce this data, compare it to the theory, do deductions, and then make predictions. And each of the phases of this will take different types of computing to do. And that I thought was an interesting note from something that came completely outside of our field. And just a note about quantum computing. So Feynman was one of the originators of this idea, and he didn't think it would be easy. But now, almost 40 years later, we still don't think it's easy. However, research in this field is accelerating. And in fact, our governments are encouraging us to actually put a lot of effort into this. Sorry. All right. Maybe I'd just go on, because I'm running out of time anyway. So, large scientific achievements in the past decades have been enabled by large advances in instrumentation. So these large silicon detectors and cameras with high granularity are driving us to large computing and data challenges. And the large costs of these projects require an international scope, which means heavy-duty networking. So what I notice is there is this very high interest in detectors. You can see it kind of dominated the poster session. But the way you get to these experimental results is through computing. And I would say that, that what John Kogut means when he says this interest should spill over to computing and software and take a page from LQCD, meaning that the LQCD collaborations, the people who wanted to get involved and promote the science had to get involved in the computing and push it forward. And I think that's what he means by taking a page from them, because the experimentalists need to be doing the same thing. So we want to think of software and computing as another device necessary to extract the science that we do. And indeed, some talks submitted to the detector were moved over to computing. So there is a little bit of overlap and maybe even confusion about what things should we live in what areas. So for instance, we had a lively conversation on algorithms and methods for jet and yuan on tau reconstruction in our session. And the large attendance at the machine learning parallels was a good sign. It shows that the community is getting engaged in these problems. So in summary, the data and compute challenges of the next decade are large and even daunting. So in order to satisfy the scientific needs of our community, we will need to build unprecedented science facilities and capabilities. The scientific harvest that is arriving with this new era of big data science and exascale computing is extremely compelling. And I thought I would leave you with the very nice calligraphy I got at the poster session. And I thought the quote was apt. It was, "Intelligence is the ability to adapt to change, and change in computing is coming."
Thank you, Dr. Kennedy, for finishing on time. So we will have time for a question.
Since there's a bit of time and you have to skip that part, I would like to know about the
quantum computing.
If you can comment on that.
Yeah. So I know a little bit more about this. I have to actually give a talk on it at the next conference I go to in 4 days. But let me just say a few things. So Fermilab is getting into quantum computing with a vengeance now. We have 4 different thrusts. So we're looking at quantum computing to solve theoretical problems in our field. And one of the things on that slide was a link to an XRF paper that we just published, and it's like an extension of lattice QCD, where you have electrons and bosons in the same, being able to be simulated in the same system. Then there is another thrust, and it was actually talked about at this conference, the MAGIS 100 detector, where you're using quantum interferometry. And that's another thrust in the whole domain of quantum information science. And then there is quantum networking that's being done. So these long-range network quantum coherence experiments. And yeah, so we're just on the threshold, just starting the research into these areas now.
Okay, thank you very much. And let's thank the speaker once again. The last talk is on industrial activities and cooperation by Dr. Petra Riddler.
So good afternoon. I have the pleasure to give you a summary on the technology applications and industrial opportunities session. And you might know that this is a relatively young session. It has been introduced during the 2016 ICHAP in Chicago to generate a bidirectional connection between industry and particle physics, covering some key topics like innovation, strategies, and across all the sectors from accelerators, detectors to computing. So in this year's conference, we had invited talks by key speakers from industry and from research. And you can see actually the lineup of our speakers here with the representation of the research institutes and the companies they came from. If you want to have a look in more detail, please have a look at obviously the Indico pages. What I will do now is I will go through the presentations under 3 perspectives. And the first one is actually knowledge transfer. So we had a dedicated presentation here by the deputy head of the CERN Knowledge Transfer Group, but it was of course also mentioned by many of the other speakers. Now, the presentation by Manuela Cirilli from CERN Knowledge Transfer was basically highlighting the transfer from CERN technologies to society, which is very nicely presented in this diagram here, where you see basically some of the key technologies that we are using across all the sectors and how they can be actually effective in applications like medical, safety, or cultural heritage. The group's mission was also highlighted basically to maximize the technological and knowledge return to society, to promote CERN obviously as a center of excellence for technology and innovation. And all this is happening by some key concepts, namely dissemination and impact. And there were quite a number of examples presented, but I will limit myself now due to the limited amount of time to 2. One was the generation or the work in the domain of cultural heritage by the construction of a compact transportable accelerator. And the story here behind is actually that in the Paris Louvre Museum, there's an accelerator in the basement, and every night some of the artifacts are basically brought down for some analysis and inspection, which is of course quite some overhead actually to do this work. Now, based on the HF RFQ developed at CERN, a portable system could be developed. And this has, of course, facilitated greatly the work of the scientists. Another example was the CERN Medicis project, which is the generation of medical radioisotopes in the Isolde facility to be available for medical research. And this was also, as you can see here, immediately reflected in the local newspapers. Now, we had 3 dedicated industry presentations by some key speakers from industry. The first one was given by Sang-Moon Lee from NVIDIA, who has also already the previous speaker highlighted, put our interest on the future of computing by combining basically high-performance computing and AI. He has lined out what are the limitations and has actually given some very nice examples what will be basically the challenges in the near future, specifically pointing out here also the 10 times increase in data volume for the HL-LHC. Now, by combining, in his view, high-performance computing with AI, we will greatly benefit in terms of accuracy, response time, and will also learn how to handle these enormous data rates. And the example that has presented was actually the unified AI and HPC platform that NVIDIA offers in this context. There was a number of examples here that were presented, and among them were, for example, things like fog forecast for the Zurich airport, but I've chosen something a bit closer maybe to our activities, which is the LIGO experiment, where the need or the possibility basically to combine multiple observational data sources was addressed by doing some deep neural network training. And it could be actually verified that the results are much more accurate and actually 4,500 times faster than with a standard CPU-based system. Then we had a dedicated presentation by Ingrid Jonak-Auer, who is the head of photosensor R&D at AMS, a sensor fabrication company or multinational company with 11,000 employees worldwide. And she has shown us actually the importance of the development of radiation-hard photodiodes for CT applications. And not only the development of these photodiodes, but actually also then the compactification and integration, so going to more monolithic solutions in this term. There is already a very successful collaboration with high energy physics by this company via a EU Marie Curie training network, which is called STREAM, which you can see over here. And there's already some work in development of radiation-hard sensors done in this field. Another aspect that was addressed in this presentation was the integration aspect, something that also in the detector building community we are working on very hard. And examples that were shown are actually the move from a 2.5D integration to a complete 3D integration, which has then, of course, at least from the commercial point of view, the advantages of a better form factor, performance advantages, and also system cost reduction, but all also parameters that are certainly also interesting for the detector community. And the third industrial presentation was given by Mekaro, a company located here in Korea, who has actually a basis in the production of precursors and heater block productions, but has a very strong team working on R&D. And they basically have shown 2 examples they are working on. One is thin film solar cells, but maybe more close to our application, the gem production. There was a very successful partnership between Mekaro, the Korean CMS team, CMS, CERN, and then the RD51 collaboration, which basically led to the possibility that now the large area gem falls for the CMS upgrade are produced at Mekaro. And from the company's point of view, this technology is of course very interesting to apply to other fields, like for example, for radioactive waste detectors or medical imaging or gem neutron detectors, to point out a few. Then we also had some presentations from the research project point of view. And let me start immediately with the first one, which was a presentation given by Isabel Bejar-Alonso from CERN on the HL-LHC industrialization and procurement. She has reminded us on the time plan and also on the importance and the need for the change of parts of the colliders and the detector. And the project structure here is very elaborate with 18 work packages covering various aspects actually of this project. In terms of challenges, What she highlighted was basically that there are, of course, time-wise challenges going within 6 years from concept to prototype. Then also short series, which basically means not all parts are produced in large quantities, which is not necessarily an attractive point for industry. So the working axis or the measures that have been taken for this project were actually to involve the industrial partners at the earliest possible moment. And it was very interesting to see also what kind of motivational measures have been taken to keep the industrial partners involved and continuously motivated to work alongside. And just some examples were shown basically of regular meetings which are happening on national and international level with the industrial suppliers. Then we had a presentation from a different angle by Myung Kwon from the National Fusion Research Institute here in Korea. He has shown us a case study which was looking at the socioeconomic impact of large scientific projects. As a case he has been using for this, the ITER project. So while I think everybody acknowledges, of course, the need for the important cutting-edge technologies that are there for such projects, what is very interesting to see is that there was a real case study done based on 10 years of data to look at the basically socio-economical impacts within 3 categories. So they have been using categories like the scientific and technical performance assessment, basically how many patents or how many publications have been made. Then the indicators of social impact assessment, for example, how many placements of students have been made in other facilities, and the economic impact assessment, translating, for example, the number of jobs that have been generated. And it was also very clearly said that the selection of what is a relevant indicator or not is rather complicated. So as Isha presented also some projects where this has been applied. And one example is the Vitrotech company, which has started off in 1955 as a rather small company, producing, for example, RF input couplers. But around 2000 got strongly involved in the R&D on accelerator nuclear fusion techniques. And basically 10 years later was in a position to supply full-term solutions basically for this field. And this is also very nicely reflected in this plot here, where you can see basically that there's a linear growth on the turnover from one year to the next, with apparently a good prospect also beyond 2020. The second example was also a local company here in Korea, Dawon Sys, which was producing heaters or power supplies and got involved in fusion accelerator R&D with the successful application now for the local metro here in Seoul. So here I will be a bit brief because this was already touched by a previous speaker. Jigao has presented to us this consortium for the industrial promotion at CEPC. Just to mention, even though it was just generated last year, end of last year, there's already 50 companies that have joined this activity. And he has underlined, as many of the other speakers, the important part that industry has played in the various stages of the project in the past, but also in the future, and here especially in the R&D phases. So to select 2 examples on that, one was the Avik Chengdu aircraft industry, where you can see here examples that they have been working on the fabrication of the main drift chamber for the BESS 3 detector, where you see the different parts, then the drift tube assembly, and then the installation in the detector. And to mention something a bit out of that is detector construction part, more in the terms of civil engineering. There's also close collaboration with the CREG company, which is one of the largest tunnel building companies worldwide, as I've learned now. And they have basically a close collaboration because there will be a number of these machines used in parallel in order to build a large tunnel like for CEPC. Then the last example, I'll come back now to a Korean initiative here, so is related to the upgrade of the ALICE ITS, the inner tracking system, which is using CMOS pixel sensors on a surface of 10 square meters. And there's a very close relationship with Korean industries in the production and preparation of this detector, and this was presented by Young-Il Kwon. So he has highlighted basically the production flow, and as you can see, the wafers that are produced at a foundry are sent basically to Korea for the post-processing. And it was very interesting actually to see that there is also interest for even small quantities, even though we might say 1,000 wafers is a lot, but for an industrial supplier this is actually not that much, to work with us on this project. The work that is being done here in Korea by these suppliers is actually the thinning and dicing of the wafers, and this is done by a company which is called Furex, which is not far actually from this location here, and which is a major supplier for commercial industry. But there's more than that that helps making actually this project. There was also a very close collaboration with a local company that produces testing machines, and there has been actually a testing machine dedicated for the testing of these pixel chips generated here in Korea, built in Korea, and is now running actually in Yonsei University for completing the tests. So that brings me a little bit too late actually to the end of my presentation. I hope I could show you that we had really a very nice lineup of speakers from industry and research institutions who have been addressing some very important key questions: which models can be used to bring developments from HEP to industry, how can we basically make this proof of concept support for upcoming technologies, and basically all the speakers have underlined quite strongly how important the international collaboration, how important the networks are actually to make this successfully. And with this I would like to close, and thank you very much.
Thank you for a very nice review and staying within time. We have time for one question. Benny.
It just was any effort made to be able to quantify the effect of our interaction with industry in actually improving the industry? In other words, we have the criticism that there's nothing much practical coming out of what we do. So I just wonder, was there any effort to try to quantify how it goes in the other way, that because we made the request to them, they actually improved in somehow that could be quantified?
I think there were actually quite a number of examples, and I'd really like to encourage you to take a look at the slides, but let me point out one which is a local example. Like I mentioned before, this Vitrotech company, which has started with the supplying of individual components like these RF input couplers, by engaging with our field, and here I mean specifically accelerator and fusion R&D, they managed to build a competence which they now can use for many applications and basically fulfill the needs to supply basically complete solutions. And if you are looking for a measurable indicator here, I think the turnover is a very good indicator. An increase, a linear increase every year basically is quite impressive. But you will find in this presentation also some other indicators like the generation of jobs that have been done by actually engaging actively in the R&D.
Okay, thank you very much. Let's thank the speaker once again.